All right, we started. Yeah. Yes, the review for the test is actually already up on the website. Okay. So you can start practicing for the test now if you'd like. And I thought about that last time. We are going to finish 1.6 today, I think. So the test would be Tuesday. So we're going to continue with 1.6, which is the last topic we need for the test number 1. So in 1.6 we're talking about logarithms, talk about the log function. Last time we went through a few rules, about 10 or so. So last time I told you what a logarithm was. It was basically a way to rewrite an exponential equation. So the first law for a logarithm was actually the definition. It means that log to the base a of b equals c means, and this was in your quiz, a raised to c equals b was the answer. Right? So that's what you should have written on the quiz. 2. We know that logs turn powers into multiple products. So if I have log to the base a of something to a power, I can actually take that power down and put it in front. 3. I know that log to the base a of a product, x times y actually becomes a sum. So I believe on the quiz there was a true or false question where I asked you, is this equal to the plus in here? And of course that was false. That's an multiplication. We know that log to the base a of a division is subtraction. By the way, there is no FYI. There is no rule for the sum.
What about distribution? That wouldn't work?
Log does not distribute. You can't, that's not log x plus log y. You cannot distribute a log. Log x plus log y is actually log of the product. 4, 5 was the change of base formula, I think, is what we did. So log to the base a of b. I could introduce a convenient base if I want, log to the base c of b over log to the base c of a. So those are the important rules to memorize. Here's the optional but recommended rules to memorize, because we're going to be using these all the time. So 6 was the fact that the log of 1 is always 0. It shouldn't be something you have to think about. But you could also derive it from this equation. We also should know that the log of 0 does not exist. It's undefined. 8, we should know that an exponential and a log will kill each other. So if I take a raised to the power log to the base a of x, that actually just gives me x. The exponential and the log will cancel. All right, that's going to help us solve equations. That's an important fact that we're going to be using later. And it works the other way because they are inverse functions, which I'll talk about. So 9 was the fact that if I have a log to the base a and I plug in an exponential function a to the x, the log and the exponential will kill each other and I will just get x. 10.
Can you explain number 8, like how that works?
They're inverse functions. Right? There's the idea of inverse functions. Right? Inverse functions sort of on does. One function will do something, the inverse function will take it and do it, put it back. So inverse functions, we say f and g are inverses. If you take f of g of x, the result is just x. Meaning g will do something and f will just undo what it did and give you back the original back. And vice versa, g of f of x is also just x. So I'm saying this works for a log and exponential. If my f of x is a to the x and my g of x is log to the base a of x, then f of g is x and g of f is x. This guy, by definition, would be f of g. Right? I have the f and I take this and I plug into the x, I get that. So because they're inverses, it just gives me that back. And vice versa would be this way. This is the g of f. It will also be x. And that's true because of this guy. The log and the exponential, they're kind of just different things. Different ways to write the same thing, where it's like you're going backwards. So one calculates when you raise to the power, the other one gives you back the power that you already raised to. So they actually reverse each other. That's going to, 8 and 9 are important because they're going to help us to be able to solve equations with logs and exponentials, which we're actually going to talk about later. The last one, this is not really a rule, it's just kind of something you need to know. Basically, if your base is e, which was that important number that we spoke about, we have a totally different notation for the log. We call it ln, or the natural log. So there are some consequences of log 10. That should be immediately apparent based on the previous rules that I gave you. So, for example, if ln of x equals y, it's the same as saying e to the y will equal x, right? By law 1, right? So like the base here is e, so it means e to the power y will give me x. It will work just like another way.
So then, does that mean it's 2.718 to 8 to the y power?
Yeah. Right. But remember, this, it goes on forever because of
Right.
it's an irrational number. So yeah, it just means this. You just write e. You don't, we won't be approximating here. So that's one thing that you should just be aware of. This means that. It's the same thing. Also, if I take ln of e to something, it just gives me the thing. If I take e to the ln of something, it just gives me the thing. That's based on laws 8 and 9. And one way you can do that, what can happen is basically, call this point 1, point 2, point 3. In point 1, what actually happens was, if you have ln of x equals y, what you can actually do, the trick is, you take each side and you plug it into the power of an exponential. So you say, I might refer to this as taking the e of both sides, right? So I take e to the ln x, by this law, this will cancel, and that will give me x, and by this it's just e to the y. Right? So you can say you take e of both sides. Or vice versa, if I know that e to the y equals x, what I can do is I can take the ln of both sides, so I can put ln on both sides. So plug each part into a log. On this side, ln and e will cancel. That will give me y, and this will just leave me with ln x. So I can go back and forth by using laws 8 and 9 in equations to plug guys in. So the basic idea is, if I have an ln and I want to solve for x, use an e. E's get rid of ln's. If I have an e and I want to solve for the power, use an ln. ln will get rid of the e, right? And based on these laws, it works for anything. So if I have like a 2 to the x equals something, then use a log to the base 2, and that would get rid of this guy and solve for x. Right? So these laws will help us solve equations. And we're actually going to do some examples. But yeah, just know that you can go back to all those previous things I wrote, and instead of log to the base 8, you can replace them all with ln's, and the rule will still work. Right? That's an important thing. And as I said, in calculus, we love using e's and ln's, so most of the time when you see a log, it's actually going to be an ln, and most of the time when you see a base, it would be an e in the calculus context. But those rules actually apply in general for any a that's greater than 1. Okay, so that was just a review that we actually talked about last time, so now let's continue. Let's talk about the graphs. So I already told you what the graphs of a to the x looks like, the exponential graph. Now let's look at y equals ln. So the graph of y equals ln x, or in general, let's say log to the base a of x, ln x will look pretty much the same. It looks like that. It passes through 1. Right? So it keeps rising, right? Kind of like a square root, not exactly, but it rises in that fashion. And it approaches 0, but it never actually touches it. It starts to go down to negative infinity. The y-axis is actually an asymptote. If you forget how it's graphed, you could actually figure it out by the inverses idea. So I know that exponential graphs are like this. This guy is y equals a to the x. And to find the graph of an inverse function, which logs and exponentials are inverses, you pretty much have the line, you switch x and y, so you're reflecting the line y equals x. If I take this and I flip it over, I will get that graph, which is y equals log to the base 2x. So exponentials look like that, logs will look like that. And of course, all your rules of transformation still hold, so if I actually graph the negative of the log, you just flip this guy upside down, and the shifts and everything will work, just like any other function. So this is what the picture of a log looks like. Log of x, that's what the picture looks like. That's going to come in handy when we're talking about limits in chapter 2. To actually know what the picture looks like. And I'll show you how the pictures help us solve things like limits later. Let's just, this is just a quick test. Nothing too difficult, just want you to evaluate these guys, get you used to looking at e's and ln's. So I'd like you to tell me, what is ln of e? What is ln of 1? What is ln of 0? What is e to the ln of x? What is ln of e to the x? And then we're going to do more examples of simplifications. Okay, what's ln of e? 1. Right? You can think of it as e's and ln's canceling each other. You can also think of it as e to the first power. And so if e's and ln cancel, the result will be that 1. So ln of e is always 1. Right? So in the same way, log to the base 2 of 2 is 1. Log to the base 3 of 3 is 1. Log to the base 7 of 7 is 1. Log to the base pi of pi is 1. Log to the base whatever of whatever is 1. What is log of 1? 0. For whatever the base is, log of 1 is 0. What is log of 0? Undefined. What is e to the ln of x? X. Because e's and ln cancel. What is ln of e to the x? Okay, what is ln of e to the pi? What is ln of e to the 17.1? Exactly. Doesn't matter what shows up in this position, ln of e to that thing is just a thing. Do some more examples of working with these guys. Simplify. Simplify the following. E to the 5 ln 2. 2 log the base 2 of 2 to the 5th. Log the base 2 of x minus log the base 2 of x squared plus log the base 2 of x to the 4 ln x squared minus 5 ln y. That's all in the power. For this one, by simplify, I want you to expand ln of the radical x squared minus 1 over x times x plus 2 squared. All of this is in the ln. So on the first test and the final, a question like this is going to come up. We're going to actually simplify things with exponentials and logs. Okay, let's begin. What's that? Well, tell me how to do it. I prefer you tell me how to do it. Can't I just cancel the ln and e and then multiply by 2?
Yes. Well, doesn't ln and e cancel?
Why can't I do that? Yeah, ln and e cancel, right? Can't I just cancel those? If I do to the 5 in front of it.
No, but it's not.
Can't you put it as e to ln to
Okay, so why couldn't I cancel the e and the ln? Because of the 5, right? Remember what did the rule say? The rule said e to the ln of something is the thing, right? Now notice in the rule, there's nothing in front of the ln. Here, there's a 5 in front of the ln.
Is there one?
Right? So, yes, there's a 1. Okay, fine. We're going to be specific. Let's be specific. The rule has a 1 in front of the ln. This has a 5 in front of the ln. If the rule could accommodate some random number being in front, the rule would have something like an n here or something to say, oh, it doesn't matter what constant is there, right? So you have to pay attention to the rules. As they are written, you have to apply them in exactly the same way. The fact there's a 5 in front of this ln is a problem, right? So now, but we actually have a rule that can get rid of that. There's a rule that says when there's something in front of an ln, I can actually bring it up as a power. So that means I can write that. And now the e and the ln are right beside each other, according to the rule, now I can cancel them. And the result is 2 to the 5th, or 32. 32 is the answer. So that's a fancy way of writing 32. Now, what happens here? So what's the answer? Here is right beside each other. This is 2 to the log to the base 2. Now we have that rule that says a log to the base a of whatever is just a whatever. Here my a is just 2. Right? So the 2 and the log to the base 2 cancel, and I'm just left with the x, which is in this case is 2 to the 5th. It's again 32. Okay, simplify this one. So see here, look at this. Log of something minus log of something else is just log of the division, right? It's this divided by that. So these first two I can turn to log to the base 2 of x divided by x squared. And now here I have log of something plus log of something. What is that? Multiplication. It means you multiply. So that's log of 2 of x over x squared times x to the 4th. And so now what I end up with is I can simplify. X squared into this is 2 times, so that's basically x cubed. Right? Or I can cancel with here, it doesn't matter. Sorry, cancel instead. But you'll end up with x cubed either way. So 2 ln of x cubed Or you can write this as 3 ln 2 of x, it's kind of the same thing. What about this one?
We have so is it x squared minus y to the fifth?
Come again?
X squared minus y to the fifth?
No.
No?
X squared divided by y to the fifth?
X squared minus y to the
Would that be like half ln squared minus?
So what was the rule we had with e's and ln's in the power? E to the ln of something is just a bit, right? There's a 1 here, and then there's something here, right? Notice that there's no plus or minus something, right? If I have minus something is a problem. How do I get rid of minus something? You could divide, right? One example, because we remember that this is just that, right? That's where your division is going to come from, laws of exponents. So this I can rewrite as e to the ln of x squared divided by e to the 5 ln y. Now what's the numerator? X squared, e's and ln's right beside each other. They cancel. What's the denominator? Y to the fifth. That 5 I would move up, and then the e's and the ln will cancel each other. That's the answer. Expand.
Would be half.
ln of the top and the ln of the bottom. In other words, what you're saying is ln of a over b is the same as ln of a over ln of b. That's not true. So you wouldn't take the ln of the top and the bottom. What does the rule say? If I have ln of something divided by something, what is it?
Subtract.
It's ln of the top minus ln of the bottom. Okay, that's the rule. Alright, so first step.
So
Minus ln of all of this. Okay, what else?
The square root would be half ln x squared minus 1.
Right, now the square root, remember a square root is actually a 1/2 power. And I will rule that so that I can bring that half down. What about over here?
That'll be minus ln x plus 2 ln parentheses x plus 2.
Too fast. X plus 2 squared, because the product means I multiply. Is everything okay here?
No, you got to put the 2, that 2, so it'll be 2.
Sure, I'll put that in the next step. Is this line okay so far? It's not okay, or am I missing it?
2.
Huh?
Two fold x plus 2.
Yeah, I'll do that in the next step.
Oh.
I already said that. We're going there. This line is not right so far. What's missing? Parentheses. Every time there's a negative sign, open parentheses. Okay, so that's going to be a minus. This is going to be a minus. Can I do anything to this? X squared minus 1. So this is actually x plus 1 times x minus 1. so now that I know that, what can I do with this? Half ln x plus 1 plus ln x minus 1. Is that fine?
No, you have to do
Half ln 1?
doesn't it have to
It does. It's parentheses. Minus ln x minus 2 ln of x plus 2. So yeah, fully expanded, this guy would be like 1 half ln of x plus 1 plus 1 half ln of x minus 1 minus ln x 2 ln x plus 2. And you might be wondering, why in the world would we want to do that? Well, in chapter 3 you'll see. There are things that I can ask you in chapter 3 where if you tried on that guy, the first guy that we started with, you'll take forever on that one problem. The whole test will be spent on that one problem, as opposed to if you start doing it on this form, it'll actually be a couple seconds and you're done. So being able to rewrite something like that, or something like this, is actually beneficial sometimes. Let's continue. Another example. Let's solve some equations. Yeah, this means final answer. Like, you can't expand anything anymore. Because we don't have a rule for a log of something plus something. Right? So if there's a sum inside of a log, you can't do anything. Let's solve some equations. A. If I have the equation ln of x equals 7. E to the 2x minus 7 equals 10. C. 3 equals 5 e to 3x. D 2 to the next squared plus 1 equals 5. What? What about the other one? What happened? You want the other one?
No, this is this one.
It's already there.
No.
What are you talking about? The board is right
No.
Push it
Okay.
to the
You go
top.
like the top.
Obviously, I want you to solve for x. X is the variable. How would I solve for x? Right, x is inside of ln. How would we get rid of ln's? E's. The e both sides. Which means that x is to the 7. That's it. It's easy.
So ln both sides.
Right. Now, my x is inside the power of an exponential. If I want to get rid of an exponential, I use a log. So I get ln both sides. That will guy. Now I have 2x minus 7 equals ln of 10. Then what? 2x equals 7 plus ln 10. And divided by 2. X equals 7 plus ln 10 all over 2. And that's it. How about this one?
my thought first.
Okay, I want to get rid of that 5 because it's in front. By ln, I'll have to deal with ln of 5 times e to the 3x. So get rid of the 5. Divide both sides by 5, I get 3 over 5 equals e to the 3x. Now what?
ln goes back.
Right, now I can ln. So that ln will kill the e. Now we get ln of 3 over 5 equals 3x, which means my x is equal to ln of 3 over 5 over 3. Now notice here, ln, you can't actually take things from outside and multiply inside an ln. So it would be wrong for me to like cancel the 3's here and multiply into this thing. And similarly here, I can't divide this 2 into that 10. It's actually illegal, right? Once you're inside that ln, you can't penetrate. So that would be the answer. Well, this one good. It's an x squared. Oh, yeah? Well, what are you reading? Yeah? Okay, how would we do that? What would be the law? So the base here is what? 2. So if I want to kill the base 2, I would use log to the base 2, right? I get to log to the base 2 of both sides. That would kill this guy. And I just have that x squared plus 1 equals log base 2 of 5, which again, as he was saying, you can use log 1 to actually get to this point. And now, subtract 1. And then what happens? Is that right? No, not parentheses. Plus or minus. So remember your algebra, it could be a positive or a minus. Here's a question for you. Does this make sense? The square root of this guy.
No.
What has to work for the square root?
Has to be greater.
What's underneath has to be greater than or equal to 0. So is what's underneath greater than or equal to 0? How would you figure out if it's greater than or equal to 0? How big is log to the base 2 of 5?
Well, it has to be a number that gives us 5, right? Raised to the power and gives us 5.
Yeah. So roughly how much is that? It is 2 point something. I know that log to the base 2 of 2 is 1. Log to the base 2 of 4 is actually 2. Log to the base 2 of 5 is actually a little bigger than 2, right? So again, there are a couple ways you can look at this. If this is the y equals log to the base 2 of x, at 1 you hit 0. At 2, you would hit 1. At 4, you would hit 2. At 5, you're going to be something a little bigger, right? So this guy here is a little bit bigger than 2, and you're subtracting 1, so it's positive. So it'll actually work. Log is an increasing function, so the bigger the number here, the bigger the log gets. So this guy is definitely bigger than 2, so it's actually fine. You're not allowed to use calculators in this class, so you're going to have to be able to eyeball your answers and know if they actually make sense, or you would have to put no solution. But in this case, that solution actually works. And that does it for 1.6. Which means S1 is a week from today.
Can you be Thursday so we get quizzes back?
You said we could choose last time.
You know, so we could review the quizzes.
Well, you should really practice from the review. Is on.
22nd
Is that the 22nd?
or the 18th?
Let me check my calendar. So yes, it will be the 22nd. September 22nd. It's a Thursday.
So we reviewed the first one, we get the first one.
Double check for that, right?
Huh?
Double check for that.
Yes, on what we've done in class 1.1 through 1.6. So things like simplifying, difference quotients, exponentials and logs, a little bit of gravity.
What's the format of the test?
It's going to be, I think, about an hour and 15 minutes long, maybe 5 problems.
5
Last
Wait, what?
So
Yeah, but there's gonna be more parts, like
review on website. The review is always already on the website, so try those on your own. You can go to the tutoring center, work with the tutor, work with them, and all that stuff.
Wait, what time are you going to provide us with the review sheet?
It's already there, it's online, it's on the website. The same place where you find the answers to the quizzes, the reviews are there. So scroll down, there's going to be a section for review for test 1, it's going to give you problems. Huh? Yes. Test 1 covers 1.1 to 1.6.
Is there a math tutor center?
Yes, it's in the syllabus, the location and the times. Yep, so that's that. We're finally done with chapter 1. So let's start calculus finally, jeez. Now we're moving on to chapter 2. 2.1 is the first section, it's talking about measuring change. And now we're going to deal with the concept of rate of change, not in its most general case, but in one particular case. So now we're getting into what calculus is all about. Rate of change. Well, half of it is. There's actually not much I want to talk about in this one. 2.1, there's basically one thing in this chapter that we're going to want to use, and it's called the average rate of change formula. And as it turns out, I said this in your quiz, although I think I made a bit of a typo, so let's actually correct that. It won't affect your answers. So here, the important notion here is the difference gives us a way to find the average rate of change of a function. what I mean is, let's say we have this function that's going on, x, y, the function is doing whatever. Here I'm at point A, here I'm at point B. A, f of B. Now I want to know, on average, how much does the function change from this point, when x is A, to that point, when x is B? On average. I don't actually care what the function does in between, you can do whatever. But overall, how much did it change from here to here on average? And the idea is, we connect that with a straight line. Because it can do whatever, but on average it's just going between those 2 points. And you basically, if you want to find average rate of change, here's where we're going to apply that concept that we had to slope. To find the average rate of change between 2 points, you just take the slope of the straight line connecting those 2 points. We did that illustration when we were talking about speed, when this guy was distance and that was time. Right? So that's the same idea. Here, the average rate of change from x equals A to x equals B is basically y2 minus y1 over x2 minus x1. F of B minus f of A over B minus A. So I actually gave you this definition. So we looked at the idea that slope could be used to measure a rate of change of a function with respect to the input variable. And so we now apply that to actual functions. Now functions don't have to be straight lines, they can do whatever, but I can use a straight line to measure what the function does on average. Over some interval, it really changes from here to here over this time period. So per unit here, I can just find the slope, and that actually gives it to me. Right? The change in the y over the change in the x. And that's telling me on average, how much is it changing? How much is the y value changing for 1 unit in the x? So it's kind of like me saying miles per hour, right? How do I change every unit of time in hours? So in general, if we were talking about the car example again, and I could say, oh, we traveled 80 miles in 2 hours, you could say, oh, on average, you were traveling at around 40 miles per hour. Because that's how you cover 80 miles in 2 hours. Now, you might not be traveling at 40 miles per hour the whole time. You had to stop at a stoplight. Sometimes you're going a little faster than 40 miles an hour. Sometimes you're going a little slower than 40 miles per hour. But on average, overall, your speed was 40 miles an hour. Right? Because that's how you would make 80 miles. And so, that's going to be an idea. And we can actually use that to predict a lot of things. I'm not going to do it now, but I just want to, I guess, mention it. Is you can use the average to kind of make plans or figure out when something is not working. So if you had a friend, you know, who lives 80 miles away from you, and you know, call him and tell him to come over, and he makes it there in like a little under an hour, and you ask him, were you speeding again? He's like, no man, I was under speed limit the whole time. I was driving very responsibly. And you know, well, I'm 80 miles away, you know, there's no speed limit that goes at 80. There's no way he could make it in an hour if he was keeping at the speed limit. Because if he was on a highway that's at 50 miles an hour, in an hour he would make 50 miles. He would never have gotten to the 80, right? So what's worse than that is you know that he had to stop at a stoplight, he had to make a turn, he had to slow down at some point, right? So he had to actually pass 80 miles an hour in the first place to even get to your house in an hour, right? So things like that you can kind of have in the back of your mind. That might come in handy in a word problems to sort of figure out the position of things and to figure out how fast something was moving. In general, the average is just that. It's the average. You could be higher or lower in between, and that's possible. But the thing is, you can never always be lower or always be higher, because the average would be lower or higher. But this is just talking about an average. You just connect the 2 points with a straight line, and the slope of the line gives you the average rate of change of that function per unit interval. Not much to say here, so let's just give you an example. And on the test, if I ask you about this, I'll ask you an example like this. I'm not going to make it complicated at this point. So I'll say something like, find, and this was actually on the quiz, find the average rate of change of x equals x squared on the interval, let's say 3 to 6. Alright, so on average, how fast is the function changing on the interval 3 to 6 if my function happens to be x squared? And I literally just use that formula. So here, notice that my interval, this guy here, is going to be my, let's write it. So that would be the question statement. Here, notice that A is always the left endpoint and B is the right endpoint. So my AB is at 3 to 6. So I know my A is 3, my B is 6, and I'm going to use that formula. So in this case, F average is f of 6 minus f of 3 over 6 minus 3. Now, what is f of 6?
36.
So f of 6 means I replace x with 6, so that gives me 36. Minus f of 3, replace x with 3, it's 9, over 6 minus 3, it's 3.
That's 9.
So 6 minus 9
27.
is 27, and then divide that by 3,
9.
so you get 9. That's it. For every 1 unit change in the x value, my y value would on average change by 9. Right? That's what the interpretation of that number means. That this means on average on this interval, every time x changes by 1 unit, y changes by 9 units. Your function could be decreasing, in which case the average would be negative. And so in particular here, I could say every time x increases by 1, y will also increase by 9. If this was a negative number, the interpretation would be, as x increases by 1, my y actually decreases by 9. So the sign would actually just tell you about increasing or decreasing in that case. And this idea is used all over the place to actually average a lot of things. I mean, a bit of a morbid example. Your doctor tells you you have 6 months to live. It's kind of, there are all these statistics that will tell him, okay, when a disease progresses this far, people usually die. And so he gives you a checkup 3 months earlier, and then he gives you a checkup now, and he says, oh, over this 3 months, this is how much the tumor grew, and on average, it's grown by this much, and so you multiply that by a certain number of months to get to this number. Hey, you have 6 months to live. And yeah, so those are all approximations. It could be greater or lower, but it's on average how it's going to change. Yes? Yes, it's always the b minus a. It's because it's really a slope. It's y2 minus y1 over x2 minus x1. So the order would matter. If the order changes on both of them, like if you have y2 minus y1 over x2 minus x1, you'll actually get exactly the same if you did y1 minus y2 over x1 minus x2. So if you change the order here, you have to be sure to change the order there. Personally, I just always do it this way. The last endpoint minus the first endpoint. Because you already memorized that formula, no point in confusing your brain. Do I switch it? I always do it that way. It's always going to be the b minus a. Just an FYI here, for define an average, use the above formula. And this will make it easier for me to talk about certain things in 2.2 or 2.3. So I'll just mention it here so you can kind of start thinking about it. But note, this is equivalent to the other difference quotient. The idea is I just rename the things. So if I'm similarly, instead of calling this a and b, I can call this x, and then call this other point x plus h, right? Where h is just measuring the distance between these two, right? So the first point is x, the next point is x plus h, which means this would give me f of x, this would give me f of x plus h. And then if I do the slope formula, I would get y2 minus y1 over x2 minus x1. X minus x is plus h. Right, so that's where that guy comes from. It's also a slope formula, so it's pretty much the same as f of b minus f of a or b minus a. I just label the things differently, and the formula looks like this instead of that. But for average rate of change, I think it's nice to think of it that way. So there's some other things that they mentioned in 2.1, but it's not important for us. That's the important idea in 2.1. Basically, that formula was the big point, them introducing that formula for average rate of change. So I move on to 2.2, but I don't think there's enough time to actually get going on that. So I think we'll end here. So test 1 a week from today, well, Thursday, after a week from Thursday, and next time we'll pick up the limits. I'll see you guys on Tuesday. Yes, we're still going to